No. Stop. Oh. Is it an odd prime? Oh, yeah, we include them too. Is it an odd prime or can it be two?
Can be two.
Okay. And that's a golden.
So we have a group of prime power order. And it has more things in the center than one. Yesterday we saw examples where the center was trivial, it just had the identity in it. It was like the symmetric group had just the identity in it, one of the examples. But if the group has the order of the prime power, then the center cannot be just the identity. That's what this theorem is saying. And it's saying it because it has a proof. And the proof is...
That is no, sorry.
Stop distracting. Just record the sound and play it later. Okay, so well, look at the class equation. So what is the order of G? It's P to the n. So this is Z. Plus there is some sum of these indices. Now they're the non-trivial you know what I mean. Conjugacy classes, yeah. They're the non-trivial conjugacy classes, so their size of these conjugacies. So this is the size of also, it's the index of a subgroup. And it's the size of a non-trivial one. So it's bigger than 1. But if it's a bigger than 1, and it's a multiple of P because this is a subgroup. This is a group which is order P to the n. So the subgroup also has order P to the n. Okay. So when you divide P to the n by P to the k, you get a power of P. P, in fact, the power of P. However, this, okay, so you add some multiples of P, or powers of P, and then you add 1, and you get P to the n. Well, that's not possible, is it? So adding multiples of P together, and you add 1, you can't get something that's divisible by P. So that can't be 1. So this says P to the n is, so if this actually was equal to 1, then is 1 plus a sum of multiples of P which is not possible. Sense, Miriam? Or which bit isn't it?
So if you accept, so let's accept that these are all multiples of the prime p. Okay? So you have multiples of p, you add them all together, and you add 1 to it. You can't get p to the end. That's a multiple of p, that's a multiple of p, so this also has to be a multiple of p. Okay? So it cannot happen that the center has order 1 if that's not a multiple of p. Why is this a multiple of p? Oh, okay. This is a subgroup of that group. That group, by assumption, has order p to the n. Its subgroup has order p to the k, of the power of k. But it's not p to the n, because these, but it's not p to the n, because these are the non-trivial conjugacy classes. Non-trivial means they're bigger than 1. So none of these numbers that we're adding here is 1. They all have to, because they're a power of p divided by another power of p, they have to be a power of p. So they're all powers of p, other than 1. They're all powers of p. That's that complete it. Okay, good. So it has a corollary. Oh my goodness. When n is equal to 2. So let G be a group of order p squared. P is prime. Then G is abelian. What is the order of ZG of the center? Well, can be 1, can it? Because of that theorem. But this is a subgroup of G. So it can be P or it can be P squared. Now it starts to be difficult. So, A, if it's P squared, then what? Yes, indeed, then the center is the whole group. So it's abelian, yes, because the definition of the center was it's all the elements that commute with or everything, and if everything commutes with everything, it's commutative and it's abelian. So then G is abelian. And the second option is that it's P. So what is the center? It's the subgroup, so it has to be cyclic, because if something is of prime order, and it's cyclic of order P. So ZG is cyclic of order P, but also the factor group we prove that it's enormous of P.
It is a normal sum. Yeah, it is. Yeah, I can't remember where we actually did it. So this is the factor group. Well, what is its order? Yeah, but they're both cyclic of order P. So I will just be writing Z for Z of G because that's shorter, and this is a coset. There has to be a coset which is a generator because it's a cyclic. And then what does it say? N. If I take any elements of the group G, what is GZ? Well, it's A to the MZ for some M, because AZ was the generator, and GZ is a coset, so it has to be the power of that coset, and this is, well, not, that would A to the MZ. Okay, so H is also a coset, so it's also just the power of the generator. It's what? H times Z. So that's a coset, okay? They're all cosets. This is a coset. The elements of that factor group are cosets. One of them is a generator, or at least one of them, because it's cyclic. So any coset is a power of the generator. But G is an element here, isn't it? And H is an element here. So G must be in the form of A to the M times something in the center. And H has to be in the form A to the N times something in the center. You better be.
Sorry about that.
Sorry. So now it's just, yeah. Now it's almost finished. So GH is A to the M, X, A to the N, Y. Now X commutes with everything because it's in the center. So it's A to the M plus N, XY. Now X commutes with everything because it's in the center, so it's A to the M plus N, Y, X. Now Y commutes with everything because it's in the center, so it's A to the N, Y, A to the N, no, A to the N, Y, A to the N, X. It's also the other, but this one's more useful because this is HG. So, G is again. In fact, it's a contradiction.
That means then that you're. So it's not just that G is abelian, it's that case just doesn't exist. Yeah?
Yeah, if you listen to it on YouTube, you will realize that as I wrote G's abelian, I said It's also a contradiction.
I did hear that, but I didn't.
Okay.
That like you didn't explain what the contradiction
No, I didn't.
was. So.
Well, you got it because you asked about it.
Yeah, but I wanted to.
So in
clarify.
fact,
Don't tell me I wasn't.
you didn't say you weren't listening. I said that I can prove that I said it was a contradiction. I didn't say that you weren't listening. Oh my goodness. You can also listen to me not saying that.
Right.
Whatever. So in fact, I think I should be taking these things more seriously than I do. So in fact, what? So in fact, Z is equal to G and not of order P. But that's not, but we don't care because the only thing we cared about was to prove that it's a video. Which brings us to the end of section 14.2. That was a nice
Little application of first nice little application of the class equation.
Yeah, which tells you that, well, we already know that if we have, we already know for a long time that if we have a group of order P, where P is a prime, it has to be cyclic. But if it's of order P squared, then it would not be cyclic, of course, because we know examples where it's like Z3 times Z3, Cartesian product, the direct product, which is not cyclic. But that's, so it's actually, that's the only option. I can imagine that being an exam, yes. Now, if you tortured me, whether it actually is in this year's exam or not, that wouldn't help because I can't remember whether it is or not. But
Well, it's just that.
but it's an example of something that I can imagine being actually prove that if G is a group of order squared, and G is a billion worth, I don't know, 8 marks or something, after, well, maybe more even, where probably part B of that question would have been state the class equation, which kind of leads you to part D, which would be the class equations. That could be it. I don't think the whole proof of the Jordan-Hilbert theory. In front is but just in time for 14.3. Called orbit counting lemma. What's that section called? Yeah.
Yeah, but we're not doing. You chose the type. Yes.
So it's called Burnside's counting theorem, which is a Brexit nationalistic point of view, because Burnside was British. However, the theorem had been known for about 100 years before Burnside, so it shouldn't be called Burnside. So let's just call it orbit counting, the orbit counting lemma. That's coming now. No, it's a short one. So, where's that attitude coming from that the only thing you want to learn is the thing?
No, it's just that this one's really long.
I mean, even if it's very long, there could be a little part taken out of it.
I'm going to say that now. In fact, it is
Okay, so what is that? So let G act on X, and XY be element of X such that they're in the same orbit. So do that. Then not the centralizer, what's it called? Tilde subscript G. I wrote the tilde first, and then I added the G to make it more precise. But yeah, it means that they're in the same orbit. So the stabilizer of X is isomorphic to the stabilizer of Y. So in particular, they have the same order. So what is GX? Missed what action? This. Okay, so the stabilizer of X is all the elements of G that now will write the action with a dot. So don't move X. And same for Y. Now, what does it mean that X and Y are in the same orbit? It means that there exists some element of G which moves X to Y. Definition of being in the same orbit. G equivalent. Now I've dropped the G's as subscripts. Okay. Now, if I take something from the stabilizer of X, then if I do the conjugation with this specific G, that's the one that, well, one of the G's that take X to Y, okay, and let it act on Y, so we have this element that acts on Y. But because of what actions do, we could, there's this kind of associativity-ish thing. It's not strictly speaking associativity because these things are not in the same set, but you can do first this, okay? We saw that if G is taking X to Y, G inverse is taking Y to X. So this is as the same thing as doing acting by GA X. And that's the same thing as acting by A first. So what does A do to X? Nothing, because it's in the stabilizer. So it's the same as acting on X by G. So that is Y. So it's that for G. So my G's and Y's are distinguishable. So that means that this GA, this conjugate element, is in the stabilizer of Y. It's what it does to Y is not. So if I take something from the stabilizer of X, with the fixed element of G, that is the stabilizer of Y, and that is the recipe for bijection. So define phi, which goes from stabilizer of X, stabilizer of Y, and it takes A to G to gang. Is that an isomorphism? What are the conditions that an isomorphism has to satisfy to be an isomorphism? It has to be one-to-one, okay? So, injective. What does that mean? Well, that means that if phi takes some A and B to the same element, what does that mean? That means that gag inverse is equal to GBG inverse. But then, of course, by cancellation, A is equal to B, so that's okay. Next. Onto. Or subjective. So if B is in the stabilizer of Y, then G inverse BG, when it acts on Y, no, and acts on X, sorry. By a similar argument as we had just before, this is G inverse B acting on GX, which is BY. What's BY? Well, B is in the stabilizer of Y, so that's Y, so that's G inverse acting on Y. G inverse acting on Y is X. So G inverse, that's like a conjugate by the inverse of G in the stabilizer of X. And what is the phi of it? It's a nice little proof, but just the Lemma. Okay, and then last thing that an isomorphism has to be. Yeah, it has to be a homomorphism. Is it a homomorphism? Well, to be a homomorphism, it would have to map F, map AB to phi of A times phi of B. Does it? Well, this is GA, GAB, G inverse, by the definition of phi. But then you can sneak in. Hello? A, A, B, yes. Thank you. Questions about this? Pardon?
I was getting
Yeah. After I'm replaced by artificial intelligence, it's not going to happen. No, I've already proved the lemma. Theorem. Okay, let G be a finite group acting on a finite set X. Let K be the number of orbits. Then K is what? The average number of fixed points. So it's 1 over order of G times the sum of all elements in G of size of the fixed point set. Correct. Okay, so that's the average number of fixed points. For every element of the group, you look at how many things it doesn't move. Because that's this. It's all points in set X that stay put when acted upon by T. For every group element, you look at how many points it doesn't move. Right? Count them all together, take the average of all the group elements, and that gives you. Proof. Who needs it? This is the crucial part of the proof. So you look at the pairs G and X, such that G maps acts maps X to X. Okay? And G is in G. All of them. Okay? Now, what's the picture? Well, the picture is this. Okay? So do a little bipartite graph. So you put G here. And X on the other side. Okay, so these are your G's. These are your X's. If X is a fixed point of G, you put an edge. So G has, say, 3 fixed points, 3 elements that it doesn't move anymore. Okay? Another element could only have 1. Another element, no. And that's the identity. Of course, the identity can move anything, so it's connected to everything. Is exactly when left element does not move the right element. If I move to the right. Now, how many edges are there? Oh, that's this. Number of edges. Like parts like that. So there are 2 ways you can count it. One of them is look at every element of G, how many fixed points, how many fixed points, how many fixed points, how many fixed points. And what you get is, for each G, you get how many fixed points, and you add them all together. But you can look at it on the other side. How many things fix me? How many things fix me? How many things fix me? So how many things do you fix? Well, that's the side of that's stabilizer, right? So the group elements that fix X, that's exactly the stabilizer. So you can look at all the stabilizer of X, their order, and add them all together by all the elements. To get them on the side. That's simple. Now, this sum, you can split it into a double sum. And the first sum goes through all O is bit. And this one goes through X is in that orbit. Well, that's the same thing because here you're adding over all the elements of X, but here also you're adding all the elements of X because everybody is in some orbit. Doesn't matter whether I look at individually or this orbit and put aside. Okay, so that's the same thing. Now, by the lemma, within an orbit, all these have the same size. That's the lemma. X and Y are in the same orbit, and their stabilizers are isomorphic. So this is just taking the same number for every element of that orbit. So that's like saying, oh, orbit, size of O, the order of Gx for some X in that orbit. This. 1411. Oh, no, 1411. It's 1411. Orbit is equal to the index of stabilizer. So this is the order of G divided by the, so Gx times the size of its orbit is P. Yes. So what you're doing is for every orbit, you get the order of G. So k orbits and k times you add together G. Good place to stop, and then you look at number of lines.